All right. All right. We start chapter 4 today on determinants. I believe that you have some experience on determinants in high school. I think also in calculus when you study change of variables, especially for functions of two or more than two variables. Okay. But the approach here is that I would like to give you an extensive study of determinants, starting from the basic properties of determinants. Just like we introduced the general vector spaces from the basic 7 axioms. So any algebraic object we can means any set that's together with two algebraic operations, addition and scalar multiplication, which is satisfying the 7 axioms, then we will call this set to be a vector space. And so we can apply the techniques we learned in the manipulation of matrices to solve questions about general vector spaces. All right, so the first section is about introduction. The introduction given in the textbook is very primitive. So here I would like to give you more extensive the study of the basic properties of determinants. Okay, and then in the next section we will prove the existence and uniqueness of determinant function. All right, so again we will use the notation m sub n times n to be the set of all n times n matrices. Okay, maybe real or complex. All right, so you encounter some of the material that the scalar can be complex numbers. Okay, all right, so the matrix may be complex matrices, but most of the time we will consider matrices as real matrices. Okay, so we know that m n times n is a vector space. So the addition is just the addition of two matrices. And the scalar multiplication is just a scalar multiplied with a matrix, just as usual. Right? And we already use the 7 axioms quite oftenly. So that's the m sub m plus m is a vector space over R over C. Right. All right, and we will fix an n greater than or equal to 2. All right. All right, and a determinant function right will be denoted by det is a function, okay, from n times n to R or to C. Depends on the scalar to be real or complex. So det is just a notation for a determinant function. right? So a determinant function, but what kind of function from the set, the vector space of all n times a matrices to the set of all real numbers, or the set of all complex numbers? Okay. We give a qualification. Yeah. So such that the following three axioms are fulfilled. Okay. So for a function from the vector space of all n times a matrix to the set of all scalars to be a determinant function if it satisfies the following three axioms. Okay, so let's describe them. So we let R1, R2 up to Rn be rows of an n times n matrix A, and alpha, beta scalars. All right. Axiom number 1, which is called an axiom about identity matrix. All right, it states that the determinant value the determinant of the identity matrix is 1. Means that we require that okay. So the value of the determinant function at the identity matrix is 1. This is called this is the first axiom. The second axiom is about replacement row operations. The determinant of a matrix, right, does not change when applying a replacement, when a replacement row operation on the matrix. Okay. So it says that R1, Ri, Rj plus alpha, Ri, Rn. Right. So remember, R1, R2, Rn are rows of A. Okay, so A, let me say here, A is here. Right? So, and when we do the replacement row operation, so here we add a multiple of I0 to the J0. Okay? This is the standard replacement row operation here. And when we evaluate its determinant value here, we find that so this is okay. So this matrix is obtained by applying this elementary matrix representing replacement operation. Okay, and the axiom says that even though we do such a row operation, the replacement operation, the determinant value will not change. Okay, this is the second axiom. Axiom number 3 about scaling. The determinant of a matrix will be multiplied by a scalar C when multiplying one row of the matrix with C, and the C can be 0 or non-zero. Okay. All right. So that's alpha. Right. So the determinant of this new matrix, because we have already multiplied the ith row of the matrix A by a scalar alpha, C, I'm sorry. So, okay. I think I some typo error. Okay, maybe I think I by alpha. With alpha. Okay, so I think it seems like I don't need the beta alpha scalar. Okay. Okay. So please correct my lecture notes. Yeah. Okay. So this is equal to alpha. The reason why I didn't use the SI alpha, the elementary matrix, is because that the alpha can be 0. When we do the scaling rule operation, we are not allowed to use non-zero scalar. Okay? Otherwise, we will get troubled. Okay, so here I return the form like this one without using the SI alpha. Okay. Okay, so if we define a function from the vector space of all n times n matrices to the set of all scalars, and we want to know whether it is a determinant function, we have to show that it satisfies these 3 axioms. All right, so let me take an example. Okay, for n equal to 2, we define a function d from 2 by 2 to r. Okay. Okay, we define a function from the vector space of all 2 by 2 matrices. Okay. As here, A, B, C, D, right? So the function value of this 2 by 2 matrix is AD minus BC. Okay. Okay, so it's indeed a function, right? So the value is a scalar, of course. Now we have to show to see if it is a determinant function or not. One. Okay, we want to find the value of D at the identity matrix. One times 1 minus 0 times 0. What? Yeah, so axiom 1 is full field. Okay, so axiom number 1 is good. Second, right? If we do the replacement row operation here, we add a multiple of the second row to the first row, right? See here, alpha C, alpha D. When we multiply the second row by alpha and add to the first row becomes to this one. Okay? All right, so this is a new matrix after replacement row operation. By definition, this is A plus alpha C times D minus B plus alpha D times C. So what is that? This is AD minus BC plus alpha CD minus DC. Okay? And you cancel them. So you see that this is AD minus BC. So this is the D of ABCD. Okay? There is another possible replacement operation here. Also, you can have AB, C plus beta A, D plus beta B. Okay? This is another possible replacement operation. And you check A times D plus beta B minus B times C plus beta A. And this is A D minus BC plus beta AB minus BA. Okay, so this is AD minus BC, and this is the D function value of ABCD. All right, so thus Axiom 2 is fulfilled. Okay, so up to now we are very lucky. And the third thing is about the scaling. Here. So AB, so suppose we scale the second row. We scale the second row by alpha. And this is A times alpha D minus B times alpha C. So this is alpha AD minus BC. So this is alpha D of ABCD. All right, the other possibility for scaling is to scale the first row. All right, so you do it by definition. So if alpha A D minus alpha B C, so this is alpha AD minus BC. And again, this is alpha. All right, so axiom number 3 is also fulfilled. So our conclusion is that since the 3 axioms are fulfilled, D from is a determinant function. Okay, so we find a determinant function for 2 by 2 matrices. Okay, so there is one. We haven't yet proved it is unique. Okay, so we find that for 2 by 2 matrices we find we construct it, right? We find a determinant function, but we don't know yet the existence of determinant function on 3 by 3 matrices. We haven't yet defined it, even though you already use that in calculus or in high school. But at least in linear algebra course, we haven't yet find any determinant functions on 3 by 3 matrices. And in general, how about n by n matrices? Can we have at least one determinant function? Because if we say that we have a 1, then we have to justify that these 3 axioms should be satisfied. Okay. Okay, so we will answer the questions in this chapter. Any questions? Okay. the task to verify the three axioms is not difficult, right? For such a function on 2 by 2 matrices. But we can imagine if you want to justify, if you want to justify a determinant function on a million times a million matrices, that's a huge matrix. Okay, and that kind of matrix will be used in engineering. For example, when you design an airplane, all right, the matrix could be 10 million times 10 million, you know. It's a very, very big matrix, but you can still handle it by using the modern computers, all right? But you can't do it because it's a long way to go, right? So we have to develop some properties of determinant functions to help us, all right, to prove the existence and uniqueness of determinant functions for any order, for any n. Okay, so that would be our jobs to do in this chapter. Questions? Okay, so it's just like an advertisement that we will show that for each n greater than or equal to 2, there is one and only one determinant function on m, n times n. Okay. Okay, but we are still far away from the goal because here we just have the result that we can find one determinant function on 2 by 2 matrices. Okay. Okay. Now we will assume that if we have a determinant function, what can we do? Okay, so that theorem is about row exchange. Exchanging. So suppose that we have a determinant function, means that a function from the vector space of all n times a matrix to the set of all scalars satisfying these three axioms. Suppose that we do have such a function satisfying these three axioms. Then we have the property here that exchanging two rows of a matrix A changes the sign of its determinant. I.e., the determinant of a new matrix by. So if you apply the elementary matrix, the permutation matrix Pij, you just exchange the I0 and J0 in the matrix A, so that this will be a new matrix. And this new matrix has a determinant value which is equal to the minus of the determinant of A. So when you exchange two rows of a matrix, then the determinant value will change the sign. Okay. Okay. So that's this is a property of a determinant function. Okay. Okay, and the proof. Is that you may have you may recall an exercise in chapter 1 that row exchange can be implemented by a sequence of replacement operation as well as the scaling operation. I hope you remember one of the exercise you did before. Okay, so here, okay, it's just a, so we, okay, so, well, I want to save my time. So let's just, okay, how to do that? The purpose is to want to exchange we want to exchange the I0 and the J0 of matrix A, right? So we want to exchange them. How do we do that? By using replacement operation as well as scaling operation. Well, first of all, we can apply replacement operation. So what is that? We just add the I0 to the J0. So that the J0 becomes to this one. And then we add a multiple, a minus of the J0 to the I0. Minus 1. So when we add the minus of this J0 to I0, we cancel Rj. So this is become to R1 and Rj minus Rj here. Okay? Because we multiply the J0 with minus 1 and add to the I0. So we cancel I, but we have Rj here, minus Rj here. All right, and then we do replacement again by adding the I0. Here, this is I0 to the J0. Okay, and we have an Ri. Okay. This is I0. This is J0. Okay, the final thing is, because this is a minus Rj, so we have to use the scaling Si minus 1. All right, so we multiply the I0 by minus 1. And so this is R1, this is Rj, this is Ri, this is Rn. So now we finish our job, right? We have already exchanged the I0 and the J0. Any questions? Okay, so now determinant of Pija. So Pija can be done by 3 replacement operation and one scaling operation. So we have Si okay. And the thing about this is a matrix here. So when you scale the ith row of the matrix by -1, then by axiom number 3, base number 3, this is -1 of determinant. By axiom 3, right? Now you apply axiom 2 3 times. You apply the replacement operation on this matrix, then you don't change anything, right? So it's Ij by axiom 2 and then we have done. So to exchange two rows of matrix A, you have to change the sign. Okay. Questions? Okay, so now some supplementary theorem. 4.1.a about equal row. If two rows of A are equal, then determinant of A must be 0. So if you have you find a matrix has two equal rows, then the determinant of A should be 0. The proof is simple. Assume that the ith row I and the jth row j of A are equal. Right? So we have this assumption. Then Pija should be equal to A. If you exchange these two rows, you will not change the matrix, right? Because they are equal. All right? So if these two rows are the same, you exchange them, will not change the matrix A. Okay? So you have this identity. Questions? All right, so this implies that you apply determinant on both sides. You get equality. But by the previous theorem, if you do the row exchange, you have to change the sign of A. So this is by theorem 4 times 1 times 1. All right, so you get the situation minus determinant A equal to the determinant A. A scalar equal to its opposite. What scalar can we have? Only 0, right? Okay, so simple, right? 4.1.b, 0 rows. If all right, if one row of A is 0, then the determinant of A should be 0. Okay. Well, that would be simple. Assume that the ith row I of A is the 0 vector, i.e. I equal to the 0 vector. And the 0 vector can be expressed as 0 times Ri, right? Okay. Then determinant A is determinant of R1 Ri Rn. Then it's equal to determinant of R1 0 times Ri Rn. Because Ri is equal to 0 times Ri. Because I is 0. Alright, so it's 0 times the determinant. So that this is equivalent to you multiply the ith row with 0. Alright, so by axiom number 3, this is 0 times the determinant of A. So it's 0. Okay? Any questions? No? All right. 4.1.c, triangular. About triangular matrices. The determinant of a lower triangular matrix right? So you have a lower triangle matrix. Now, for any lower triangle matrix, the determinant value will be the product of the entries in the diagonal. Right, and this is the same for upper triangle. So this is the upper triangle matrix. The determinant of this upper triangle matrix will the same, which is the product of the diagonal entries. For the textbook, this property is used as axiom number 1. Okay, as axiom number 1. But for me, I think because if we want to justify a function defined on n times a matrix to be determinant function, the 3 axioms should be as simple as possible. Otherwise, the task of justification will be a little bit difficult than complicated axioms. So I purposely to replace this axiom as just the identity matrix. Okay, so it's much more easier for us to justify whether the value of a function at the identity function to be 1 or not. Okay, so but we still can get this property. All right. So my purpose is that I further simplify the 3 axioms. All right, simpler than the one given in the textbook, and that will facilitate myself to prove the uniqueness and the existence property of a determinant function. But the price paid is that I have to show this is a theorem, a property we can have from the 3 axioms. Well, but that's fine. Okay, we can do that. All right, so proof here. All right, so there are 2 cases. To consider. Right, case 1. All diagonal entries AII are non-zero. All right, that is simple. Why? If, for example, here, if we have a low triangular matrix and all the diagonal entries are non-zero, what can we do? We can use the replacement operations to eliminate all the off-diagonal entries, right? I believe you already have this experience before in chapter 1. Okay, so you can use the for example, A11 can be used to eliminate all the entries. Why? Because you have all 0 here. So when you do the replacement, you will not affect anything here, because here you have all 0s. That is the nice structure of lower triangular matrices. Okay, so you use the first row to eliminate all the entries, non-zero entries here. So they become all zeros. But when you do the replacement operation, you will not change the value of the determinant, right? You will not. Okay? So you will not change when you do all the things, the determinant value will not change. Similarly, once you do that, this is 0 already, right? Then you will use the 0, A22, all zeros to do the row replacement operation to eliminate all the entries here. Okay, and one by one. So I just say after a sequence of replacement row operations, so let me show you. A11, 0, A21, A22. Okay. Right, so now by replacement row operations, you end up with A11, 0, okay, you get here. And then you this time you will eliminate the rest of these entries by A22. Okay, so keep going on. You get A11, A22 up to ANN, and all zeros. Okay, and all these are Axiom 2, Axiom 2, Axiom 2. Okay, so we apply Axiom 2 there. All right, and now we're using the Axiom 3, the scaling axiom. So this is equal to A11, 1, 0, A22, okay. So it's just like you multiply the first law by A11. Okay, so by axiom 3, you get A11 here. And similarly, you get A11 times A22, 1, and 1, H and N. So again, this is Axiom 3, and you so you get A11, A22, up to ANN, and the determinant of 1, 1, 1. Okay. This is Axiom 3. But this is identity matrix. So by Axiom 1, the determinant of the identity matrix is 1. So this is A11, A22, ANN. Because of Axiom 1. So by using X1 to 3, we get the result we have for the lower triangular matrix. How about upper triangular matrix? Well, in here we use forward elimination, right? But for upper triangle matrix, we use backward elimination. Okay, so we start here. We use the last row to eliminate all the non-ideal entries above ANN. Okay, and then use the last second row to eliminate all the entries above n-1, n-1, etc. So you do the backward elimination. Okay. So let me quote. After a sequence of replacement row operations, backward elimination. Okay, so the determinant all right. So we do the backward elimination. Okay, and finally, you get so they are Axiom 2. Okay. And similar to that, this is A. Three. Okay, so we have that. Okay, so I make it short because this is a similar argument to that. Okay, if you want to know the detailed proof, you just see my lecture notes. That the lecture notes is very accurate. Okay, very detailed. I try my best, but I have to save time in my lecture now here. Okay, so we have a common data case number 1 that all diagonal entries AI are non-zero. Okay. Now, case number 2. Okay, so there is a 0 diagonal entry. All right. Now we for a lower triangular matrix. Okay, for a lower triangular matrix, we let AII be the first 0 diagonal entry. All right, so the situation is here. A11. So here, this is ith row, and here is the ith column. All right, so the AII is 0 here. This is the first 0, and all the AJJ. Okay, so AII, so that's AJJ is not 0 for all J less than equal to I. Okay, so all these entries are non-zero. So they are non-zeros. Okay, they are non-zeros. Now, with non-zeros, we can eliminate, use A11, right? To eliminate all the non-zero entries up to AI1. Okay, so we can eliminate them to 0. So this is become to 0, right? Okay, and so by forward elimination, this becomes to A11. So you can eliminate because this is 0, right? All right, so you can eliminate and all zeros. right? But don't care about the entries below it. Don't care about them. Just up to here. You use the first row to eliminate the entries here, up to the ith row here. So here is the ith row. Now you have, right? Now the second row have 0 entries except A to 2. So use the second row to eliminate all the entries below it. Okay, up to here. So what happened? After you do such things, the ith row becomes to the 0 vector. So Axiom 2. And this is equal to 0 by theorem 4.1.b. You have 0 row. Okay? Right? So it's 0. Questions? So here is by forward elimination. Okay, so we can cancel, we can eliminate all the to 0, okay? Zeros. Whoa. Okay, my time is, I have a couple of minutes. Anyway, so this is 0. And then this is A11 up to AII up to ANN, right? Because this is 0. So the product of the diagonal entry is 0. Okay, so the lower triangle, the determinant of this lower triangle matrix is equal to the product of these diagonal entries. Is 2. The value is 0. So we have this one by forward elimination. How about upper triangle matrices? So for an upper triangular matrix, we let AII be the last be the last 0 entry. The last 0 diagonal entry. So that's AJJ not equal to 0 for all j greater than I. So that the determinant of A11, A12 up to ANN, A22, Okay, so this is I0. Okay, so again, this is I0. And in here, that they are non-zeros. So we can eliminate all the entries up to here. Okay, so by backward elimination, so AN will cancel all the non-zero entries up to the I0. Left behind all the entries. Don't touch them. Just up to here, you cancel them to zeros. And then use this to eliminate all the entries up to the I0, etc. So that's all this. So you have all zeros. Okay, and now the I0 becomes to 0, 0. Okay. And this is axiom 2. So this is becomes to 0 again by theorem 4.1.b, and this is A. Okay, and we have done. So both cases are there. Okay. All right, so we finished the proof that for triangular matrices, okay, the determinant is equal to the product of their diagonal entries. Okay. Okay, so I stop here, and you have to prepare for quiz number 6.